0.25.
5?
0.25
0.25.
to the power of 10 to the power of negative 3.
10 power negative 3.
Yes.
And plus
J10
J10.
plus 1.
And
Plus 1.
plus 1.
J10 plus 1 is in bracket.
Oh, I couldn't get you. Plus J10. So what is the imaginary value? Class?
It's 0.05 plus J 0.5.
Wait, I have to admit. So again, 0.05
plus J 0.5.
0.5. All of you got the same answer? PU, eh? So this is the per unit value for the line between T1 and T2, right? Okay, now what is the ZPU for the load? The actual value 300 divided by what is the Z base at zone 3? Since load is connected at zone 3, this is 400 76.1 eh. So what do you get? The Z per unit for the load.
.63.
0.63 PU.
Yes.
Okay. Anything else that we need to change to the per unit value? So our aim is to change all the impedance, or all the old per unit impedance into new per unit impedance. Yes, since we have 1, 2, 3, 4 impedance for this circuit. We have impedance for T1 in per unit, all per unit. This one for the transmission line, this one for T2, and the next one, or the last one is load, right? So we have found the Z per unit new for line and load. Now we have to find what is the new per unit value for the T1 and T2. Okay. Okay. So you see the T1 and T2 is given in all per unit, right? The X is given in all per unit value, not in actual value. You see, per unit, PU. This one also PU. So how to find the new per unit value? Remember the equation? Z PU new equal to Z PU all times KV all over KV new, right? All base voltage divided by new base voltage square, don't forget square, times the MVA new over MVA old, right? So this is the important equation to relate the new per unit value with old per unit value. And see here? Okay. X T1 PU new equal to what is old value 0.1 times KV old. What is the new, what is old base voltage? You can choose either
Either one,
right, primary
yes.
or secondary. If you use the primary, so you have to use the new base voltage at the primary lah, right? The primary is 13.2 kilovolt. If you choose at the secondary 132 kV, so you have to use the base voltage at the new base voltage at the secondary, which is 138. At primary is 13.8 kV, the new base voltage. Let's say I choose at the primary one, so KV old is 13.8 divided by, sorry, the old value is 13.2 right here, 13.2, 13.2 divided by new is 13.8 square MVA new 10, right? 10 MVA divided by old is 5, right? 5 MVA. So what do you get?
$0.183.
J 0.183.
183.
183,
Yes.
PU. Okay, don't forget J, again, don't forget the imaginary component, J. You have to put J lah, since it's X, right? And J 0.183 per unit. So this is the new per unit value for T1. So for the line we have already calculated. Then we go for T2. X T2 PU equal to
0.08. J 0.08.
okay, you put J lah, don't forget J, 0.08. The old voltage, let's say old base voltage, let's say I choose at secondary, so secondary is 69, right? So the new base voltage at secondary is 69 as well, same, right?
Yes.
Okay, so you can cancel lah. This one 10 divided by 10 also, so you cancel, you get
J 0.08.
J 0.08 PU. So means that the old per unit value equal to the new per unit value, since the base old and base new are similar. So done. So we have done transferring all the impedance in per unit value. So what's next? Draw the reactance diagram lah, right? Because we want to do the analysis. I want to find what is the current, the current, what else? The question asks to find the current, right? Generator current, line current, load voltage, and the load power, right? Okay. Then you can draw the reactance diagram. Okay. Okay, this is the reference, This is the reference. So grounded, right? It's a reference. So this is the VG, the generator voltage. This is the XT1. This is the Z line. This is the XT2. This is the ZL load. Okay, we already know the per unit value of the impedance of the circuit. What else is given? You see, The generator voltage is given, right? The nominal value, 13.2 kilovolt. So this is the actual value of the generator voltage, 13.2. So we can find what is the VG in PU, right?
Yes.
So what is VG in PU? Actual value 13.2 kV divided by what's the base value?
13.8.
13.8 kV. So what you get? 0.96
6.
PU. So we can calculate the per unit value of the generator. 0.96 PU. So next, what else? You can calculate the IPU, right?
Yes.
Straightforward, VG divided by Z total. So what do you get? 0.96 divided by J 0.183 plus what is the new per unit for the line? The new per unit for the line 0. 0.05 plus J 0.5, correct? Please check. (0.05) plus J 0.5, and then plus what is the XT2? J 0.08, right?
Yes.
And then last one for the load. What is load?
0.63.
0.63, right? So this is the total impedance. Looking from the source lah. Similar as a circuit theory. So what is the IPU? The per unit current. What do you get? What is IPU? Make sure you familiar with this complex number manipulation. So what is the per unit value? Class, what is the per unit value for the current? The answer here is, what is the answer? 1.35.
Yes.
1.35 angle minus 26.4. Did you get?
Wait.
1.35 angle minus 26.4.
Yes.
Sure. Same, right? In per unit, all the current flow through this circuit is the same, right? The series circuit, right? So the current flow in the primary and the secondary of the transformer, is it similar?
Yes.
The current flow in the primary and the secondary side of the transformer. The actual value of the current. Is it similar? The per unit value is similar. However, the actual current, is it same? The current flow at the primary and the secondary of the T1, for example. At the primary and the secondary of the T2, for example. The actual current, is it same?
No.
No, right? Why? It's differ? Because the base current is
Line impedance.
equal. It's not same, right? Base current.
Yeah.
The base current for the primary and the secondary is not the same. And that's why the actual current will be differ.
Okay.
Eh? The per unit current is okay, same. Since in per unit representation, remember we already removed this coupling circuit of the transformer, right? There's no longer coupling circuit of the transformer. It's become a single impedance, right? XT1 here, and also same for XT2. So do you get this per unit current? The answer is correct.
Yes. Yes.
Okay.
Yes.
Now, after getting this per unit current, what's next? The question asks to find we have done this, right? IG, PU, IT line, PU, I loop PU is same. In actual value, it's not same, right? So we can find the base current for each zone. Base current for each zone. Okay? So how to find the base current for each zone? For example, I base zone 1. Remember, current equal to base divided by root 3 times V base, right? It's a line-to-line voltage, right? That's why we have this factor, root 3, right? It's a three-phase power, So what is S base? Always give the new value, right? 10 MVA divided by root 3. What is the new base voltage at zone 1?
13.8.
13.8, right? 13.8. Always use the new base value in finding the base current. Always new base value. Not old value, new base value. Well, you get the I base for zone 1?
418.4.
For?
18.
4.8.
488.4.
488.4.
No.
Huh?
418.4.
418.4. Right, okay. Other check, So IB for zone 2, same, 10 MVA divided by root 3, whereas the new base voltage at zone 2 is 138, right?
138.
What is the new? What is the base current for zone 2?
41.84.
41.84. Right. So IB for zone 3 equal to 10 MVA divided by root 3 times new base voltage is 69, right? So what is the new base current?
83.67.
83.67. 0.67. Okay. So after finding this base current, so you can find what is the IG, for example, actual, right? Equal to IGPU times I base, right? Times base in zone 1 is 418.4. So what you get? So what is the I generated actual?
Five six four.
Hmm?
564.84
564.84
angle
minus
26.4.
36.4, right?
Yes.
Angle doesn't change, right? Actual current is ampere, Okay, and then let's say I okay, IG actual correspond to the also equal to the I T1 primary, right? Correct? Is it same? Primary for zone 1. Correct. Okay. Okay, I T1 secondary actual equal to what? I T1 PU times, so what is the base current in zone 2? 41.84. So what do you get? You should get 56.484 angle minus 26.4, right?
Yes.
Right. The unit current is same, right? The difference only the this. This is the current at the secondary of the T1, the actual current at the secondary of T1, which correspond to the transmission line current, actual line current. This one correspond to I line actual, because the same base. And also you can find what is the actual current at the primary of T2 by multiplying with the base current here, the base voltage, the base current here, zone 2. This one also equal, right? This one also equal to I T2 primary. Same. The actual current of T2 at the primary is same with the line current and also the secondary current of the T1. Then the load current in actual, I load actual equal to PU, I load PU times the, what is the base current in zone 3? 83.7. So what you get? The actual load current what is the actual load current? Did you get? So this is the base current for each zone. The actual load current is not given. So you have to calculate. So what is the actual load current? Plus
112.93.
huh?
112.93.
1, 1,
Two.
2,
0.95.
0.95. Angle same, right?
Yes.
Oh, sorry. (112.9) minus 26.4. So this is the actual load current. So what else? So we already calculate all the current on each zone. V load and P load, right? So what is the V load? The load voltage. So V load PU equal to I load PU times Z load PU lah, right? So what is I load PU?
112.95.
I load PU.
112. Sorry, wait.
1.35
1.35. Check angle.
negative 26.4
0.4 times Z load PU.
0.63
0.63. So you get
0.85
0.85.
05
Right. PU, right. So what is the load actual? 0.85 angle minus 26.4. 0.85 times the, what is the base, new base value at load side? What is the new base voltage at zone 3 or at load side?
69.
69
69K.
Okay. So what do you get? Class, what do you get?
58
5?
8650
5.650 kilowatt.
and 5860
5 60
no point
48.5
48,650
0.6 lah 0.65 kV. Right. Did you get the VPU and actual load voltage? Okay. All right. Then P load, PU. What is the equation for finding the real power and power? I load PU square times R PU, right? So what is I load PU? 1.35. Remember, for finding the real power, we only use the current or the magnitude or phasor current. The magnitude, right? Only consider the magnitude, because the real power, the magnitude of the current, so meaning that 1.35. So not consider the angle, only the current magnitude. I squared times what is RPU? 0.63, right? So what do you get?
1.15
1.15 PU. So only take the magnitude of the current, since this is the real power. power being transformed from the electrical to heat form, right? Non-electrical form. Then P load actual equal to 1.1. Sorry, my screen suddenly blank. Sure, let's try again. Can you view my slide?
No.
It's frozen, doctor.
It hang. Problem with this. Now, can you view?
Still stuck.
Just stop. Okay, let's try again.
Yes, doctor.
Okay, let's try. Otherwise, let's try.
Yes.
So P load actual equal to 1.15 times the base, right? What is the base power? It's 10, right? 10 MVA. The S base equal to P base equal to Q base, remember? In per unit value. So what you get? 11.5 kilowatt. So this is the actual load absorbed by the load. So any questions so far? I think we have done this example problem. Any question? What 11.5 is acceptable. This one is 1.14, 1.15 is okay, acceptable. This is the per unit voltage. Sorry, per unit power. Since this is only the purely resistive, so the base, the MVA, the MVA or the apparent, the complex power is equal to the base, equal to the apparent power or the real power, right? It's similar, 1.14 or 1.15, you get 1.15. Then you multiply with the base power, you get the actual value. Any questions so far? Before we continue with the advantages of the per unit system. Any question, class? Okay.
Okay,
Okay.
So far tak ada je.
Okay. Okay. So let's go to these advantages of per unit system. So the per unit system is the scaling mechanism, right? So the transformer equivalent circuit can be reduced or can be simplified by properly specifying the base quantity. So means that there is no more coupling circuit for the transformer. So we can simplify the transformer as a single impedance, which give a clear idea of the relative magnitude of various quantities such as voltage, current, power, and the impedance, the electrical quantity lah, the clear representation. And also it can avoid or making the serious calculation error when preferring quantities from one side to the other side lah. So we know that the unit values of the transformer at the primary and the secondary are same, right? And then per unit impedance of the electrical equipment of similar type usually fall within a narrow range in per unit system. So we can express the voltage closely, almost the same, because 0.95 is, for example, 0.98 is close, right? Rather than in actual value. So let's say, for example, for single phase voltage, the nominal value is 230 volt, and the acceptable range or tolerance is plus 10 minus 6 volt. By expressing this voltage in per unit, it is much easier to express the voltage or to identify the condition or the status of the voltage rather than the actual value. So the manufacturer usually specify the impedance of the equipment in per unit. As I said, from the nameplate rating, so all the values are in all per unit value. So in the impedance can be expressed in per unit or in impedance or actual value based on the rating of each component. Okay, why use this per unit system instead of the standard SI unit? And these are the reasons. It's same, right? So when the value are expressed in per unit, the comparison of the electrical quantity become straightforward with respect to their normal value. So for example, a transient voltage reach a maximum of 1.42 per unit. You can see here, if you express the voltage in per unit, 1.42, so means that the voltage condition is 42% above the nominal value. Rather than you have to calculate the actual value, right, correspond to its tolerance. And then the value of the impedance expressed in per unit stay fairly constant, whatever the power and voltage rating, and tend to fall within the narrow range. Okay, for example, all transformer in 3 kVA, so this is the capacity of the distribution transformer to 300 kVA power range, and the leakage impedance varies approximately 0.01 pu and 0.03 pu for this rating. Whereas the winding resistance, so this is the leakage reactance, X. So this is the R, the winding resistance, will vary between this value, 0.01 and 0.005 pu in any values of the nominal voltage. So in case of the transformer rating of 300 kVA to 300 MVA, it's a bit larger lah. So the reactance, the leakage reactance value will vary approximately between this range, 0.03 and 0.12 pu. While for the winding resistance, it will vary between 0.005 and 0.002. It's much more smaller lah, right? So same case for the synchronous machine or salient pole machine. So the synchronous reactance or XD, the reactance of the synchronous machine between this range 0.6 and 1.5 pu. Whereas in case of sub-transient reactance, this one depends on the fault study lah. If we are interested in the sub-transient fault current, we have to use this sub-transient reactance, which is much smaller. The reactance is much smaller, right, between 0.2 and 0.5. So this is the value of the impedance or reactance for various fault studies condition. This one during the steady state, and this one during the sub-transient condition. So it means that if you do not know, the parameter of the, for example, 10 kVA transformer. So by assuming the average value between this 0.02 and 0.0075 for winding resistance is not cause a major error by having the per unit values in the impedance in per unit value. Okay, we can summarize that the per unit value simplify the calculation when all impedance in a multi-level voltage are expressed on a common power base. Remember, only one reference or one common power is selected. And nominal voltage at different network. So the nominal voltage or the new nominal voltage depend on the turns ratio of the transformer, right? If we have transformer, we have to bring the new base at the primary to the secondary using the transformer turns ratio. Okay, any questions so far? Nur Fateh, why so late? Now almost 1 hour. Okay, so we have done the per unit values in old version of in new version of notes. So this is the old version of the lecture note. This same. The previous is the new version of my lecture note. So you can read this one, the old version. Maybe we can go through the example. The theoretical is almost the same. You can read. This is the starting from the page 55 until end is the old version of the per unit notes. So you can read by your own. Maybe we can go for the example. The previous is the new version of the lecture note. Okay, this is how to obtain the reactance diagram from the one line diagram. Have you tried this example? Class? Maybe we can try this.
Yes.
Okay, let's see. You are given the whole rating of each component. So we have one generator, two transformer, and one load. So this is the nominal rating of all values of the generator, 10 kV, all base value. This is the all MVA, 100. So this is the generator impedance. In this case, we are given the generator impedance, 0.1 plus J0.8 ohm. So this is the all, or this is the actual value, the actual value. So we have the transformer T1, first transformer. So this is the rating, 10/20 kV. So you see here, this is 10 referred to the primary, 20 is referred to the secondary. So this is all MVA 150, and this is the transformer impedance. You can see here 0.2 plus J0 plus J1 ohm. So the impedance of the transformer referred to 10 kV. So what is the difference between this and the previous example? The transformer impedance now is given in actual, right? Previous is given in all per unit. This time the impedance is given in ohm. the actual value. So if the transformer is given in ohm, so it should state the reference, means that this impedance referred to low voltage side or refer to the primary side. You see, refer to the primary side. So the transformer refer to the secondary will be differ lah. It's not same. Which is based on the transformer turns ratio, right? Remember, as I said, if you want to bring all the quantities at the secondary to the primary, the impedance, you have to multiply with the square of the turns ratio, right? For the impedance. For example, Z2 prime, the secondary quantities refer to the primary, so you have to multiply the secondary impedance by the square of the turns ratio. Okay, this is the impedance referred to the primary. 10 kV, right? Okay, this is the line impedance, which is same as previous, the old base voltage, the old MVA, and the actual line value lah, 0.5 plus J2 ohm. And this is the transformer 2, you can see here, this is the primary 20 kilovolt, 10 kV is secondary, the old nominal value, or base value, 150 is old MVA, so the impedance is referred to secondary, you see, 0.2 plus J1 at 10 kV side, at the secondary. And the last is the load, load is 10 kV, the old value, base value, and then the actual value of the load. Now the load is impedance. It's impedance with real and the imaginary. In previous, it's only real part, right? Okay. Okay, again, so you have to find what is the ZPU for each component. Okay, before that, what is the reference? Is it any reference here from the question?
No.
No, or you just draw the single line diagram, Okay. This only draw the single line diagram and then find the reactance diagram. Okay, never mind. I think we can go for the example which has the reference voltage lah, or reference power. This one. Same. Okay. Okay, this one exercise you can try. If you have any difficulties, you can let me know. You can post to the forum and then WhatsApp me. So I go to the forum. And then, for example, okay, never mind. We go later lah. For example, then we go through this impedance diagram. So any question in finding this impedance diagram for this example?
No.
You can draw the source, and then with the impedance, I think you can put like this lah, better, right? Okay, and then for transformer, so, and then for transmission line, okay. And then for T2, T2, and then the last one is for load, right? Okay, it's simple, So this is the reactance diagram lah, So this is the VG. So this is the ZG. This is the Z T1, Z line, Z T2. And this is the Z load. Okay. Any question in drawing the reactance diagram?
No.
Simple, right? So this is the generator, and this is the load, right? And usually, one should be taken as a reference lah. So meaning that if you are given the generator voltage, so you can find what is the current lah. Similarly, if you are given the loads, for example, the voltage across the load, then you can find the current as well. And depend on the question. So you can choose either one lah, depend on the question given. Okay, so this is the rectangles diagram. We have 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. 5 impedance in series. So each component is represented by its equivalent impedance lah. Okay. This one also same. Obtain the impedance rectangle diagram. So this is the impedance diagram. So in this case, we have two generators. So we have two generators. So you can draw the impedance. Better use the rectangles lah. Since you want to analyze the circuit based on the rectangles impedance, by ignoring the equivalent circuit, right? For example, the transformer, the magnetic circuit has been removed. This one for the generator, and then 41. And then for line 42 for generator 2. Okay. Okay, VG1. Let's start again. Don't know why lah. This okay, the German also have this Rosoff suddenly it's not so stable. They use the whiteboard. It's okay. Just one whiteboard.
Share with Echo.
I think I opened my Jamboard. Where's my Jamboard? Where's the file? Right? So this is the coupling circuit of the transformer, with primary impedance or reactance 1 ohm and the secondary is 2 ohm, right? Okay, let's say I bring to this quantity to primary. Let's say refer to primary. So X to prime equal to what? The secondary reactance referred to the primary equal to X2 times A square, right? Times square of the turns ratio, So equal to 2 times turn ratio 10 over 20, right? Square. So what you get? The reactance referred to the primary, the secondary reactance referred to primary, 1 over 4 times 2. So you get 0.5, correct? So the X this is x1 total. J 1.5 ohm. Right. So can you refer the quantity to the secondary side? So what do you get? Can you try? Refer to secondary. So what is the x1 prime? Plus, so what is the x, the reactance referred to the secondary side of the transformer, x1 prime equal to x1 divided by a square, right?
A squared.
Remember? But divide by the square of the turns ratio. So this is the primary quantities referred to the secondary. This x1 we bring to the secondary. So 1 divided by 10 over 20 square. So what do you get? Four, right? Did you get? Now x1 referred to secondary. Equal to x2, x2 total equal to J2 plus J4, right? You get J6 ohm. Okay, this is the impedance referred to the secondary. Okay, previous is referred to the primary. So what is the per unit value? X PU, let's say primary equal to, so what is the actual value? 1.5, right? Refer to the primary, J 1.5 divided by X base, right? So what's X base at primary? X base equal to 10 square over
20.
Yep. Over 100, right? So what you get? X base at the primary, the base voltage at the primary divided by the base power lah, which is 100, right? What you get? 1, right?
1. Yes.
So this one equal to J 1.5 PU. Okay? Now, yeah, yeah. X PU secondary equal to J6 divided by, what's X base? What's X base at the secondary? So X base equal to 20 squared over 100.
100.
Right.
Yeah.
What you get?
2.
2. For,
No. Wait.
20 square over 100.
4.
4,
Doctor,
Yep.
me and Asil Basalam still cannot access the Jamboard, okay?
You can access the Jamboard.
Yeah.
2 ohms. So this is nominal value, the voltage and the power. Then what we have done is to bring you can see the primary and the secondary reactance. So in making the equivalent circuit, or in removing the coupling circuit, we have to bring this quantity to the primary, either primary or secondary. So let's say we refer to the primary first. So I bring this secondary reactance to the primary by multiplying square of the turns ratio. So 2 times square of the turns ratio, 10/20, right? Square, I get 0.5, J 0.5 ohm. Now the total reactance looking at the primary. So what I get, this one is the existing primary reactance, 1 ohm, J1, plus J 0.5. So I get J 1.5 lah. So this is the equivalent circuit referred to the primary. So any questions so far? Any questions so far?
No.
Okay. So I divide by this. Okay. Okay, now I refer to the secondary side, meaning that all the reactance at the primary transferred to the secondary by dividing square of the turns ratio. So this is the basic relationship lah. So I divide the primary reactance 1 by the square of the turns ratio. So I get 1/20/10/20 squared. So I get 4 ohm, right? Then this is the total reactance referred to the secondary by adding the existing secondary impedance J2 plus this is the referred reactance to the secondary J4. So we'll get J6 ohm. So this is the total reactance referred to the secondary lah. Then what is going to be done is to find the X per unit primary at primary side and also at the secondary side lah. We want to prove it. The X PU for the transformer at primary equal to the X PU at the secondary. So for primary side, the actual value is 1.5. You can see the previous, right? This is 1.5 here. The actual value or total value divided by the base value. So this is the base reactance, which equal to 10 square over 100 volt. So 10 is the base voltage at the primary, 20 at the secondary, right? So you get 1, J 1.5 divided by 1, you get same lah, 1.5 PU. Then for secondary side, J6 is the total reactance referred to the secondary here, J6 divided by base. So what is the base reactance at the secondary? 20 square, the voltage divided by 100. So you get 4. So J6 divided by 4, what do you get? J 1.5, right? Same, right?
Same.
So we can conclude that for transformer, the per unit impedance at both sides are same. At the primary or secondary, similar. This is what the example is about lah. To see the impedance of the transformer, 1.5, right? Okay, 1.4, 1.5, same, right? Okay, this is the equivalent circuit in per unit lah. So 1.5 per unit. So far, any question before we proceed with the next example? Example 5.1.
No, Doctor.
Okay. You have to quite hurry lah. Okay, in example 5.1, a single phase. You see the question? A single phase. So read the question properly lah. And not always 3 phase. Some question they ask for single phase value. A single phase 2 winding transformer is rated 25 kVA. So meaning that this is the single phase or 3 phase voltage power. 25 kVA.
Single.
This is one phase, right? Because a single phase two winding transformer. So single phase apparent power is 25 kVA. One phase, not three phase. And then 1100 or 1.1 kV stroke 440 volt. Okay, this is the line to line voltage or line to neutral or phase voltage. This is the VLN.
Line to neutral.
Phase voltage lah, because it's referred to the single phase.
Yeah.
So this is the VLN, same as well. So VLN. This one at the primary or at HV side, high voltage side. This at the secondary side. So this is the phase voltage. So frequency 50 Hz, okay, as usual. The equivalent leakage impedance of the transformer, the XL, referred to the LV side is 0.06 angle 78. Okay, this is the XL. The XL at LV, right? Or at secondary lah, LV side at secondary, 440 volt is 0.06 angle 78 ohm. You see, this is the old reactance lah, actual, the actual value in ohm. Okay, using transformer rating as a base value, determine the PU leakage impedance referred to the LV side and also to HV side. Okay. So again, we have to find the X base, right? X base at LV side. So what X base at low voltage side? 440 square over 25 kVA. So what do you get? All of you can access this Jamboard.
Okay.
So what is the final answer? The base reactor, the 440, the voltage at LV side, square divided by base power, which is 25 kVA.
Yes.
So what is final answer?
7.74.
7.74 ohm, right? Okay. All of you got the same answer,
Yes.
AXL PU on LV side equal to 0.06 divided by 7.74. What do you get? What do you get?
Uh, 0.075.
0.075 angle 6 angle same, right? Correct. 0.075.
Oh, sorry, 0.0775.
Check, other check. 0.000.
07. No. 0.077775.
Yes. Yeah.
0.0
0 775.
775. Right. Okay, this is the XL PU on LV side. PU lah. Actually not X lah, Z You change to Z lah. Because X only imaginary, right? You change to Z lah. Not X, Z lah, impedance, Alright. Z. Because consists of the real and the imaginary, right? So Z. Okay? All of you got the same answer? Okay, now, so what is the question asked to find also the per unit implication impedance at HV side, right? Okay, what is the ZLHV equal to? So how to find the ZL at HV side? You are given the impedance at LV side. If you want to bring to the HV, in this case HV at the primary or secondary? HV side in primary or secondary?
Primary.
Primary, right? So you have to multiply by square of the turns ratio, right? Correct?
Yeah.
This one LV lah. Low voltage side, ZL LV side. All right. So you get, you bring the secondary quantity, or the LV quantity to the primary. So you need to multiply by square of the turns ratio, So what do you get? 1100 over 440, 440 square multiply with this value, ZLLV. What do you get? What do you get, class?
0.375.
0.375. Angle same, 78. Right. Boom. All you got the same answer, Then ZL PU HV equal to 0.375 angle 78 degree divided by, okay, what is the Z based on HV side? Z based on HV side equal to 1100 squared over 25k VA. What do you get?
48.4.
48.4 ohm, right? So divided by 48.4. So you get ZL PU on HV side?
Same answer.
Same answer, right? Should be same, Okay. Transformer, right? Okay. Any questions so far? You should get 7.74 times 10 power minus 3. Same, right? 7.74 times 10 power minus 3 is 7.74. 1, 2, right? Should be 2, 0.
One more zero.
It should be
One more 0, right?
Yeah.
Right. One more 0, eh?
2 0.
Check, should have 2, 0, right? After decimal.
Yes.
So don't make this silly mistake, Should be 0.00, right? The answer is correct, right? 7.74 times 10 power minus 3, right? Okay. So 0.00775. All of you got the same answer? Or any questions so far? Before we proceed to the next example. Okay, find the per unit value for each component and draw the rectus diagram. Okay, this one I think the previous example. Okay, now it's given, right? The base parameter for the system are at generator, and see? So one component is taken as a reference, which is generator. It's mentioned in the question. So the base voltage for the generator is, the voltage is 10 kV and the power is 100 MVA, which is similar with the old value, you see? The old value and the new value now same. So this is the new value and this is the old value, right? From the nameplate. Okay. Again, we have to find what is the new base voltage for each zone, as usual. So this is the first step. So we have to find the new base voltage for each zone. Because we want to find the per unit, right? Okay, this is the zone 1. Z1, the zone 1. This is the zone 2. Z2. And this is the zone 3 lah. Z3. From the generator to the primary of T1 is considered as a zone 1. From the secondary of the T1 to the primary of the T2 is a zone 2. Starting from the primary of the T2 until end of the load is a zone 3. So you are given the new base. KV new is 10 kV. MVA new is 100, right? So it's referred to generator, right? From the question. Refer to the generator. So this is the reference. So this is our reference generator. So meaning that you have to transform from the upstream to the downstream in getting the base voltage. Because you are given the generator as a reference. So you have to bring all the quantity from the source or from the upstream to the downstream. So here, Z1, zone 1, what is the new base voltage? Given, right? 10 kV. Zone 2, so what is not equal, is the equal is will be confusing, right? Yeah, right. Okay, VB Z1, base new, is 10 kV. VB Z2. What is VB Z2?
20.
20. How? Get 20?
V1 over V2 equal to
Ah,
over V2.
okay. VB for zone 2 is 20, right? You see here the ratio 10, 20, right? Okay. So let's say V1 over V2 equal to 10 over 20. V1 is 10 volt, right? 10 kV, right? So you find to V2.
Yes.
V1 over V2 equal to transformer ratio is 10 over
10 over
20.
10. 10 over 20.
This is the V1, right?
Yeah.
Already known. So V2 equal to V1 times
Times.
is 2, right?
Yeah.
2. So you get 20 kV lah. It is 20 kV. Okay. So V base for zone 3. What is the ratio for the T2? You see here 10, 20. So 10 refer to primary or secondary?
Primary.
Huh?
Secondary.
10. You refer to the primary or secondary?
Secondary.
Huh?
Secondary.
Here. This one. You see here? 10, 20. So you can swap, right? Because this is secondary 20 kilovolt. So means that primary should be rated at 20 kV, which is similar with the secondary of the T1.
Yes.
So here is V secondary is 20 kV. Sorry, V primary is 10 is
Primary is 20.
V primary, not secondary, primary, right? Okay. Okay, V primary or V1 lah, Either I write V1. V1 equal to 20 kV and V2 equal to 10 kV. This one on the HV side lah. This one on the LV side. Right. Now it's okay, right? Load is 10 kV, which correspond to the secondary of T2, which is 10 kV. Okay. So you can swap the turns ratio of the transformer corresponding to the suitable value lah. And they say T1 is, for example, 18 kV, the secondary. Is close to 20, right? So this one also should be 20 on the primary and the 10 refer to the secondary. Otherwise, it's not logical. It's 20, this one 10. How come, right?
Yeah.
Okay, V base on zone 3 is so same. You want to find again? Let's say V1 over V2 equal to 20 over 10, right? 20 over 10. So in this case, V1 correspond to 20 kV, right?
Yeah.
So V2 equal to V1 is 20 kV, 20 divided by divided by 2, right?
Yes.
Right. You get 10 kV.
Okay.
So here is 10 kV. So this is the new base voltage. It's important, to find the new base voltage for each zone. Any questions so far?
No.
No, eh? Okay. Now, after finding the new base voltage, you can calculate lah. So, what is the ZPU for generator? Equal to old value 0.1 plus J 0.8 divided by, what is the Z base value on zone 1? 10, right?
Yes.
10 kV. ZPU T1 or TX1. You see, the impedance is referred to 10 kV side, 0.2 plus J1 divided by, in this case 10 kV refer to the LV side or primary side. So what is the base voltage at primary side? Same, right? 10 kV, same as above, right? So you get the ZPU T1. ZPU for line, transmission line here, the old value is 20, right? This one also the old power, MVA. So the actual is the 0.5 plus J2, 0.5 plus J2 divide by, what is the new base voltage here at zone 2? It's 20, right? Right?
Yes.
20, 20 kV. Okay. And then ZPU T2. It's also given the impedance referred to 10 kV. In this case, 10 kV at primary or secondary?
Secondary.
At secondary, right? Okay. 0.2 plus J1 divide by, you have to refer to the 10, which is secondary. So what is the secondary new base voltage?
10.
10, right?
10.
Okay. Divided by 10 kV. Okay. Okay, what is the final answer? Okay, ZPU for generator. Did you get? Sorry, this one not the, sorry. I put the base voltage, not the base voltage. Should be the Z base, not the voltage. Sorry. Not the base voltage, the base impedance. Sorry, so to calculate the base impedance. Okay, before that, find the Z base. the Z base. Z base 1. This one Z base. So transformer refer to 10 kV side. Okay, Z base 1 also same. Z base 1. For line is Z base 2 lah Z base 2 at zone 2 base 1 at zone 1 lah This one for ZT2 refer to the 10 kV at the secondary so this one also at zone 3 lah, Z base 3, right? Okay, before that, what is ZB1, ZB2, ZB3? We didn't calculate yet, right?
Yeah.
Okay, ZB1 equal to
B1 squared.
B1 here B1 is here.
Yeah.
This is the zone 1 zone It's a zone 2. This is zone 3. Right? Okay. Okay, BB1 equal to
B squared over SB.
equal to 10, right? 10 kV squared over
100 MVA.
100, What do you get?
One.
Huh?
1.
1, 1 ohm.
1
1 ohm. Z base 2 equal to 20 kV squared over 100. 4, Right? 4 ohm.
Yes.
Yes.
ZB3 equal to 10 kV squared over 100.
1.
1. Alright. Okay, this one should be supposed to be ZPU for generator divided by Z base 1. Same, right? Divided by 1, you get 0.1 plus J 0.8. PU. Okay, 41. Transformer 1. Since the impedance referred to the primary, so you have to use the base at primary lah. This one also divided by 1, should get the same answer. 0.2 plus J1 PU. ZPU for line, for transmission line, 0.5 plus J2 divided by, what is Z base for zone 2? 4, right? So what do you get?
0.125
0.125 plus
0.5 J
0.5. Okay. And for transformer 2, since the impedance referred to the 10, which is at the secondary side, so you have to divide by ZB at zone 3, zone 3, Z base at zone 3. So zone 3, 1, right? So you should get the same answer lah. 0.2 plus J1. And the last one, load, right? Okay. So load, ZPU load, LOAD equal to 0.2 2 plus J3, eh? Zero point two plus J3 divided by load at zone 3, right? Divided by 1. Should get the same lah. 0.2 plus J3. PU. Okay. So let's compare the answer. The same. 0.1 plus 0.8, 0.2 plus 1, for line 0.25, 4.125 plus 0.5, 0.2 plus 1, and load 0.2 plus 3. Okay, correct. So, any questions so far in finding the per unit impedance? So, after getting this per unit value, new per unit value, then we can substitute into this reactance diagram lah. In this reactance diagram. And again, it depends on the question. So we can use either one lah, whether the generator or load as a reference. So meaning that you have to determine the load current lah. You have to determine the load current by knowing the value of the generator voltage or load voltage. Find the load current, actual current in every component, and voltage drop if the load voltage is 1 pu. You see, in this case, the voltage at load is given, right? Meaning that load is taken as a reference lah. So the load voltage is 1 pu, then we can straight away find the current by dividing voltage with the total impedance. The total impedance. Make sure this is the complex number. Make sure you use the correct value lah. It's a complex number. So the exact total, so you end up with 0.33 angle minus 86.2 pu. So as I said, the load current through this circuit is same, right? The load current is same. Even we have the transformer. So the load current will be same. So the difference is actual current. The actual current at the primary and secondary of the transformer is different because of the different value of the base current. Okay. The voltage drop, same, right? After finding the current, then we can find what is the voltage drop across each element by multiplying with the impedance lah. V equal to Iz. So you can find what is the drop, the voltage drop across this synchronous generator impedance across each element lah, each component by multiply with the by their respective impedance. You can find the voltage drop. Okay, this is the base current. The base current for each zone lah. Base current for each zone. We have to find what is the base current here. So I base at zone 1 equal to, what is I base at zone 1? Base MVA, 100 MVA divided by root 3. Since this is a 3-phase, right? 3-phase or single phase?
3.
See the question? Single phase, you see? Single phase, right? Is it the continuity of the example or? Oh, sorry, 25. This one is different from the previous, right? 25, 110. Yeah, this one different. Okay, this is a 3-phase, 3-phase. The 3-phase here. Okay. Three-phase, so root 3 times what is the new base voltage at zone 1 is 10, right? 10 kV. So you get the IB1. So IB2 is 100 MVA divided by √3 times what is the base voltage at zone 2 is 20, right? 20 kV. You get the base current at zone 2. IB3 equal to 100 MVA. So S base remain, use the new base value as given. Divided by √3 times 10 kV, right? The new base voltage at zone 3. So you should get 5773.5 for zone 1. This one for zone 2 and this one for zone 3. It's similar, right? Zone 1 and zone 3, the same. So the actual current, you multiply lah. The base current with the per unit current. So the per unit current will be same for each component. You see 0.33 angle minus 86.2, same, right? And the only difference is the base value. You see, it's different. So this is the actual current, actual load current. This one is the actual line current, and this is the actual of the generator current. And then voltage drop, same. Multiply per unit current with the impedance, IZ lah. You find the impedance. Impedance is given, right? From the calculated value. I also is from the calculated value. This one for generator. Then you can calculate also the total generated voltage. This is the generator, total generated voltage. By sum up all the voltage drop across each element. So this is the load per unit voltage. It's given, right? 1 per unit for load. It's given here. Load voltage is 1 pu. So you add up all the voltage drop across each element to get the generated voltage. So you get 2.12 angle minus 3.5 pu. And again, multiply with the base value of the generator, which is 10 kV, right? So generator is located at zone 1. So you get the actual line-to-line voltage for the generator, which is much more greater than the nominal value, which is 10 kV, right? So this is the reason, due to the excessive of the voltage drop, the significant voltage drop in the component of the system. Okay, any questions so far? Sorry, I took your time, 5 minutes, 3 minutes more. Any questions so far? So you can try with another load value, 50 plus J100. Only change the load and then calculate all again. You can try by your own. Next on this Wednesday, we continue with this another example. Okay. Question 3. So far, any question?
No.
Before we stop?
No.
Any question before we stop the meeting?
No, sir.
No, doctor. Thank you.
Okay.